Hey everyone, welcome to this explainer. Look, if you've been working with containers, you already know the absolute magic of getting an app packaged up and running locally on your machine, right? But there is a massive leap between a basic single container running locally and a resilient, highly available production-grade workload running in Kubernetes. Today, we're bridging that exact gap. We are going to demystify how you take a functional app and layer on the configurations that make it robust, self-healing, and secure. To do this, I want to introduce you to our protagonist for today, Taskboard. Just take a look at this UI. It's incredibly minimalistic. Just a simple task list. It's definitely not winning any design awards today, but hey, don't let the simple front end fool you. Our mission in this explainer is to transform the infrastructure powering this basic app into a highly secure, zero-downtime, self-healing system. We're going to take it from a fragile local project right to a battle-hardened Kubernetes deployment.
So here is our roadmap for the journey. Phase 1, deploying the Taskboard app. Phase 2, building its immune system with self-healing probes. Phase 3, executing zero-downtime deployments. And finally, Phase 4, locking it down with essential security best practices.
All right, let's just dive right into it. Phase 1, deploying the Taskboard app.
To actually get our application into Kubernetes, we have to speak its language, and that means relying on declarative YAML manifests to tell the cluster exactly what we want. Now, a true production-grade deployment cleanly separates its configuration from its code. You'll notice here we're using a ConfigMap to handle our non-sensitive settings, things like the API port and the database host, but right below it, we have a Kubernetes secret. This is absolutely crucial. We've all heard the horror stories of developers accidentally committing their passwords to GitHub, right? Total nightmare. Instead, we use secrets to securely inject those credentials, like our database password, directly into the environment at runtime. Okay, so once our config is securely stored, we can go ahead and spin up our backend. Notice how this PostgreSQL database deployment brings everything together. It references the exact config map and secret we just talked about to populate its environment variables. It seamlessly pulls the database name, the user, and the password without any of that sensitive data ever touching the application's source code. Oh, and it also attaches persistent storage. So even if this database pod happens to crash, our users' tasks won't just vanish into the ether. So just like that, the foundation is complete. We have successfully deployed a 3-tier architecture. We've got a Postgres database retaining our state, a containerized REST API backend processing the logic, and an Nginx static web UI serving up the front end. Pretty awesome. But right now, Kubernetes only knows if these container processes are turned on. It doesn't actually know if the application inside them is working properly. Let's fix that.
Moving right along to Phase 2, Kubernetes self-healing probes.
This phase is where we literally build the application's immune system. We need to teach Kubernetes how to check our app's vital signs so we can react automatically when things go wrong. Take a look at this new probe section we've got highlighted. Here, we're pointing Kubernetes straight to our API's health endpoint. We're basically telling the cluster, hey, hit this endpoint on port 8080 every few seconds. If you get a success response, we're golden. If you don't, take action. By explicitly defining these readiness and liveness probes, we are transitioning from blind hosting to truly intelligent orchestration. Now, it's really important to understand the distinct roles these two probes play. Think of a liveness probe as a pulse check. If your application deadlocks or crashes and fails this check, Kubernetes brings out the defibrillator and aggressively restarts the container. Bam. A readiness probe, on the other hand, is a bit more chill. It's like a waiting room. Say your database briefly goes down. Your API shouldn't completely restart, it just shouldn't receive user traffic for a minute. So, if the readiness probe fails, Kubernetes safely stops routing traffic to that pod until it recovers. The absolute best part about all this? You don't need a pager going off at 3 a.m. for a transient database error. If a pod crashes, let's say due to an out-of-memory exception, the Kubernetes ReplicaSet detects that missing pod immediately. Without you doing a single thing manually, it spins up a replacement to maintain your desired capacity, uses that readiness probe to wait until it's fully booted, and then seamlessly routes traffic back to it. It is completely self-healing, saving you a ton of stress and sleep. Which brings us to Phase 3, zero-downtime deployments. In the old days, pushing a new version of an app meant putting up one of those maintenance pages and just crossing your fingers. But in Kubernetes, releasing a new feature shouldn't drop a single user connection. You essentially have two main strategies for evolving your app here. The default is a rolling update. It's gradual and it's built right into Kubernetes. It spins up a new pod, waits for it to be ready, kills an old one, and just shifts traffic piece by piece. But sometimes you want complete control. You want to test the new version in production before any users actually see it. For that, we use a blue-green deployment. This is basically like having a stunt double for your application, giving you an instant, switch-flipping cutover. Running a blue-green deployment is this beautiful, precise, four-step choreography. Step 1. While your users are happily using the current, let's call it the blue version, you deploy the new green version right alongside it. Step 2, you run your validation tests directly against those green pods. Step 3, and this is the magic moment, you switch the Kubernetes service selector to point to the green version, which moves all the traffic instantly. And finally, step 4, once you're 100% confident, you just retire the old blue version. If we look directly at how that switch actually happens at the code level, check out this label right here, color green. Remember, both deployments are running simultaneously in the cluster. Our load balancing service was previously looking for pods labeled color blue. By simply editing that service configuration to look for color green instead, Kubernetes instantaneously repoints all user traffic to the new version. And the best part? If a bug suddenly pops up in production, there's absolutely no panic. Rolling back is literally as easy as changing that text back to blue, instantly reverting your users to safety. All right, we have made it to our final stop. Phase 4, Essential Security Best Practices. Up until now, we've really been focused on keeping the app running, right? Well, now we have to focus on locking it down. In Kubernetes, security isn't just some firewall you bolt on at the very end. It's expressed as configuration right alongside your application code. Just look at this YAML block inside our deployment spec. This is called the security context. By default, containers often run as the root user, which is a massive security risk. Here, we are explicitly telling Kubernetes to run as user 1000, a non-root user. We disable privilege escalation, and, incredibly importantly, we enforce a read-only root file system. Meaning, if an attacker manages to exploit a vulnerability in our API, they can't download malware or alter our system files because the container's disk is literally locked and read-only. No way! These settings act as our production armor. We run as non-root, we use role-based access control, or RBAC, to make sure our API pod only has permission to read the exact config maps it needs and absolutely nothing else. We can even enforce pod security at the entire namespace level. That way, the cluster just automatically rejects any deployment that tries to run with escalated privileges. By applying this principle of least privilege, we have officially transformed our fragile local app into a completely locked down, highly resilient production system. So there you have it. From cleanly separating configurations, to self-healing probes, to zero-downtime routing, to hard-coded security contexts, you have just seen exactly what it takes to make an application truly production-ready. You have conquered the local cluster architecture. But this leaves us with one final very exciting question. Now that you have this completely resilient, secure, automated workload, are you ready for the cloud?